Welcome to the Foundry by Forge College. Okay, let's just jump straight into it today. We are about to embark on what is essentially the ultimate digital moving day for your Solana architecture. Now, if you've been tracking with us in the Advanced Solana Concepts track, you know we've been doing some serious heavy lifting with timekeeping. Well, today, we're focusing on data storage enhancement strategies. We're going to use this explainer to figure out exactly how to pack up all our digital boxes without completely breaking our backs, or, our network. So here's the game plan. We'll be hitting the storage dilemma, how to shrink data on-chain, moving it off-chain, distributing state, real-world trade-offs, and then finally picking your actual strategy. Let's get moving. All right, Section 1, the blockchain storage dilemma. To set the stage here, we established our operational schedule back in our previous lesson, infrastructure coordination patterns. We nailed down our time anchors and our schedules. But now that the schedule is set, we actually have to pack the boxes. We've got to decide where all this data is going to live. Now, proof of history is an absolute marvel of engineering, right? It makes our blockchain incredibly fast because it creates these deterministic time anchors. But there's a catch. Because it's so incredibly fast, it's kind of turning our network into a digital pack rat. It's hoarding massive amounts of data at lightning speed. Every transaction, every state change, every smart contract interaction, it all adds up. So where does all this data actually go? Because if we just leave it all sitting on our critical path validators, they're literally going to buckle under the weight. Which brings us to Section 2, shrinking data on-chain. Look, our very first instinct when we have way too much stuff is usually just make the stuff smaller. So let's look at this first packing strategy, squeezing things down natively right there on the network. The actual mechanism for on-chain compression is fascinating. You're tightly packing fields together, or you're storing what we call data-encoded change sets. That's really just keeping a log of what specifically changed instead of copying the entire file over and over again. Honestly, think of this exactly like vacuum sealing your clothes so they fit perfectly into a carry-on suitcase. It dramatically shrinks the overall account byte sizes, and you never even have to leave the house. But as you know, in engineering, there is absolutely no free lunch. It's all about trade-offs. This strategy is brilliant for immediate reads because the data is sitting right there in the validator state. You get incredibly low latency. You want it? You got it. But the trade-off, your processor is going to sweat a bit. It'd have to constantly zip and unzip that data every single time a change is made. Still, if you're building an app with high reads but moderate rates, this vacuum sealing method is fantastic. Moving on to Section 3, moving data off-chain. What happens when you've got items that simply cannot be vacuum sealed, like a digital grand piano? If vacuum sealing just isn't going to cut it, we have to look at moving those bulky items entirely out of the house. And that brings us to hybrid on- and off-chain designs using content-addressable storage. Instead of forcing the data on-chain, your on-chain account just stores a tiny cryptographic digest, a hash. That hash acts as an unforgeable pointer, directing you to a massive, bulky payload safely sitting in an off-chain archive or object store. It's exactly like renting an off-site storage unit for your heavy furniture and just walking around with the paper receipt in your pocket. Your on-chain footprint stays tiny, though you do have to factor in off-chain storage and egress costs. But hey, what if you don't fully trust a single off-site storage unit? Well, then you'd use a distributed archival method called erasure coding. This involves splitting your payload into fragments and parity sets, and then scattering them across multiple archive nodes. Imagine taking a backup of your highly secretive diary, shredding it, giving the pieces to 10 different friends, and designing it so mathematically you only need 6 of those friends to hand their pieces back to reassemble the whole diary. It gives you incredible durability across geographic regions without bloating the local validator's storage. Of course, recovering that scattered diary takes real coordination. When a node restarts or needs to recover, it goes through this multi-step process. The validator syncs, you coordinate the fragment reassembly, and then, this is absolutely crucial, you perform an integrity check. You use your proof of history ticks to coordinate this multi-step handshake. By anchoring fragment retrieval directly to specific snapshot ticks, you ensure everything reconstitutes at an exact, known logical point in time. All right, Section 4, distributing and sharding state. Let's keep building on this. What if the house itself is just too small, no matter how efficiently we pack or how much junk we throw in offsite storage? Well, in that scenario, we have to fundamentally restructure the property. We do this through state sharding, which means partitioning the address space. You basically split the house into duplexes or maybe even an entire apartment complex. Now, each validator is a specialized landlord that only has to manage their specific rooms or shards. During leader scheduling, transactions are routed only to designated shard owners. This makes read latency within a single shard incredibly low. But the trick here is that any action needing coordination across different shards, like a resident moving from apartment A to apartment B, requires intense alignment with our proof of history ticks. Otherwise, you get cross-shard races. And look, along with restructuring the property, we need some good old-fashioned housekeeping, namely pruning and compaction. This is basically coordinated garbage collection to expire historical versions of state. Think of it as simply throwing out old junk you no longer need. But you have to time this flawlessly. These background compaction processes must be tied perfectly to poached tick windows. You do not want to accidentally toss out anything critical right while an indexer is trying to take a snapshot. Section 5. Real-world storage trade-offs. Okay, abstract concepts are great, but let's ground this. Let's see how these packing strategies actually apply tangibly to something like a massive NFT marketplace. Check out this incredibly practical multi-strategy blueprint. If you are minting high-res artwork, you want to keep the minting and ownership transfer incredibly fast, right? So you only keep the core ownership and a content hash natively on-chain. Then you push those heavy, high-res metadata blobs completely off-chain to a distributed object store. But what about the users? They need to see thumbnails instantly when they load the marketplace. So you keep those thumbnails in a low-latency cache right next to your RPC nodes. You're combining immediate on-chain verification with off-chain bulk storage and near-node caching. It's the best of all worlds. But here is the critical point. What happens when things break down? Those local thumbnail caches, they're ephemeral. If an RPC node crashes, that cache just disappears. When the node finally recovers, it has to rebuild that cache from the off-chain archive. You absolutely must anchor this archive rehydration process directly to your POH snapshot ticks. At tick N, the node ticks a snapshot of the ownership pointers, and then fetches the heavy objects. If you don't lock this to a specific time anchor, you end up with a severe split-brain scenario. Your on-chain pointer says you own the art, but your local cache serves up a completely different image, or maybe no image at all. Which brings us to Section 6, choosing your storage strategy. We've covered a ton of ground here, and it's time to bring it all together so we can weigh operational simplicity against actual storage efficiency. I want you to treat this matrix right here as your cheat sheet. As you progress through our programs and courses within the Forge College community, use this table to map out your exact service level agreements for reads, writes, and recovery. Notice how on-chain compression gives you the absolute lowest read latency, but it requires that synced compaction window. Or look at erasure-coded archives. They provide phenomenal durability, but man, they come with high integration complexity for fragment retrieval. You really have to score these strategies against your own specific component dependencies. So let's distill this entire explainer down into 3 golden rules. First, always prefer patterns that shift complexity away from your critical path validators. Second, favor on-chain representations when you absolutely need immediate, consistent reads. And third, ultimately, any strategy that changes your state representation, whether that's compaction, pruning, or pointer finalization, must be strictly locked to a POH check. That is literally the only way to keep the entire network in perfect sync without risking data corruption. And that brilliantly illustrates our storage playbook. Remember, data storage isn't just about saving space. It's about optimizing how your entire network breathes, coordinates, and recovers. So I'll leave you with this provocative thought. As your own Solana decentralized app scale to millions of users, are you going to keep trying to vacuum seal a grand piano? Or is it time to restructure the entire property? Make sure to check out forge.college to dive deeper into this subject and map out your next move. Thanks so much for joining me on this explainer, and I will see you in the next one.